Excuse me. So I want to show you guys something here really quick to kick things off. So this is one of the limitations of the comparators that we talked about in our last class meeting. Actually, let me flip this back up so I can do things. So what I have here, right here is a comparator circuit where my input signal is just a simple sinusoid, but I've added some noise on top of it, okay? And I'm going to run a simulation, and I want to show you what our output looks like as a function of our input voltage. So I'm just going to run this really quickly. So here's my input signal with a little bit of noise. Okay, so it's just a signal that's ranging from 0 up to positive 10, down to negative 10, with a little bit of noise on top. So we can very clearly see that that's a sinusoidal signal with just a little bit of wiggle on our waveform. When I look at my output, this is going to go kind of berserk. Okay. So I have these spots right here, and I'm going to kind of zoom in on things in just a moment. But essentially, my reference voltage in this case is 3 volts. You can see that right over here. And so if I have a noisy signal, because I have a comparator where I'm comparing it to 3 volts, whenever it's ever so slightly above 3, it swings high. And whenever it's ever so slightly below 3, it swings low, much like we saw in class. But if we have a noisy signal where there's variation around our reference voltage, it causes it to ring like this, which is probably not a good thing in a lot of applications. So what we're going to do today is we're going to talk about how we can use positive feedback to get that ringing to go away so that instead of having a noisy output signal like that, so let me just delete this V out up here, we might have a nice clean output signal that doesn't take into account that ringing. Okay. So that's the goal for today, is to figure out what positive feedback is, what it does, and then how we can apply it to make what's called a Schmitt trigger. And then we'll also talk about how we can apply it to make simple oscillators. Okay. Okay. So the first thing that I want to talk about for today, um, this overall lecture is positive feedback op-amp circuits. And we are going to start with an introduction to feedback systems. From a signal flow perspective, and then we'll move on to specifically op-amp related things here in a moment. So I'm going to draw a signal flow diagram for a feedback system in general, okay? So over here on the left-hand side, I'm going to put X sub S, okay? So this is my signal that I'm starting out with, okay? So this might be the output of a sensor or something like that. And that signal is going to be passed into some sort of summing mechanism. And I'll give these fancier names here in just a moment. So I'm going to put a sigma here. And this is an arrow. And I'm going to continue along in what's called the forward path. And I'm going to put a block right here. And this block is my open loop amplifier. And I'm only drawing it as a rectangle so that I have space to write the words open loop amplifier inside of it. If you choose to draw it as a triangle, that won't hurt my feelings. And this open loop amplifier is going to be characterized by some open loop gain, AOL, right? So if this was a voltage amplifier like an op amp, we would have this as a VOL for the open loop voltage gain, one of those parameters that we can read off of our data sheets like we've talked about previously. Okay. Now out over here, I'm going to draw a little point. And then way out here on the right, I'm going to have my output signal Y. So if we didn't have that little summer thing right there, that's what that sigma sign means. This is essentially the circuits that we've been dealing with. This is an open loop configuration. There is no feedback. So what I'm going to do now is I'm going to introduce my feedback system. Okay. So below that block for my open loop amplifier, I'm going to put another block here that is representative of my feedback network. So this could be literally, might just be a wire, but it could also be resistors, capacitors, and inductors, or networks containing those components, okay? So this is my feedback network. And it's going to have some parameter K. Okay? And what I'm going to do is I'm going to take my output signal and feed it into my feedback network, like so. And then the output of my feedback network is going to be fed into this summer as well. And I'm going to put some mathematical symbols on here really quickly. So I'm going to put a plus sign up here representing that this signal X sub S is always going to be added. And then I'm going to put a plus and a minus sign down here, meaning that this feedback signal could be added or subtracted depending on what we want to do. If we're going to have positive feedback, it's going to be added. Negative feedback, it's going to be subtracted, but we'll get into that in a little bit, okay? So now I'm going to do a little bit more labeling of things here just for the sake of stuff, okay? So this spot right here along our signal path, this is the input to our amplifier. So I'm just going to label this here as amplifier input. And for right now, I'm going to label a signal here, X sub I. This is what's commonly called an error signal, okay? And I'm going to say that it is equal to X sub S, and then I'm going to add some stuff to that in a moment as we follow our signal around, okay? Over here on the right-hand side of this guy is where I have my amplifier output. And my output signal Y is just going to be this amplifier's open loop gain, AOL, acting on that error signal, XI. So I'm just going to write here, AOL times X sub I. Okay. This portion of my network right here is the input to my feedback system. So I'm just going to write feedback input. So the only thing that's going into that is literally my signal Y. So I'm just going to write that down there. And over here is my feedback output. And it's going to generate some signal X sub F, which is just K times our output signal Y. And now coming back around here, I get that plus and minus, so I can really see that my error signal, X sub I, is going to be X sub S the signal I'm trying to process, added to or subtracted by my feedback signal x sub f, like so. Okay. So this is a basic block diagram structure for a general feedback system, okay? Where our feedback system contains 4 different parts, okay? So the first part is what's called a feed-forward system. And our feed-forward system is an amplifier characterized by its open loop gain. Okay. And I'm just going to draw a little arrow here that this open loop amplifier is my feed forward system. The second part of my feedback network is going to be my sense mechanism. Where the sense mechanism is a system or network that measures the output signal. So for this particular block diagram, this node point right here constitutes our sense mechanism. The third thing we have is a feedback network. I've already labeled that guy, so I'm not going to have to do that again. So this is a network of components characterized by a feedback factor K. And then lastly, I'm going to have some form of return mechanism. Goodness gracious, that looks like shit. And the return mechanism is a system or network that combines the feedback signal x sub f and the source signal x sub s to generate the error signal x sub I, okay? And the positive sign or negative sign of this combination of signals is going to determine whether we have a positive feedback system or a negative feedback system. And we'll go into that in more detail now. All right. So let's talk about a positive feedback system in particular. So in this positive feed, yes.
Just go on and go feedback. A little more of it. Oh yeah, that.
So we've got the feed forward system consisting of our amplifier, the sense mechanism, that is that output node, our feedback network, which I was already labeled, and I guess actually I should label this guy right here as our return mechanism, which I didn't do a moment ago. So thank you for that. Okay. So we're going to consider a case for today where the sign on the feedback output is positive. Okay, so we're going to be adding those guys together. So if I look at my output signal here of Y, it is going to be AOL times X sub I. And now I'm simply going to substitute in for X sub I, XS plus XF. So AOL times XS plus XF. But I also know that my feedback signal XF is just K times Y, my output signal. So I'm going to substitute that in as well. So I have Y is equal to AOL, my open loop gain, times X sub S plus K times Y. And so what I'm going to do now is I'm just going to play around with this a little bit, and we're going to get an equation that tells us how this system behaves. Okay? So I'm going to distribute that AOL, giving me the relationship Y is equal to AOL times X sub S plus AOL times K times Y. And now I'm going to move all of the Y terms to the left-hand side of the equal sign. So that's going to look like Y minus AOL times K times Y is equal to AOL times X sub S. If I take that factor of Y out of both of those terms, I get Y minus AOL times K is equal to AOL times X sub S. And now I'm going to define what I'm going to call my closed loop gain. ACL. Let me just put a little note here. Closed loop gain. And that is going to be the ratio of my output signal Y divided by my input signal X sub S, which in this case is going to give us our open loop gain divided by 1 minus our open loop gain times our feedback factor of K. And so from this, I can see that my closed loop gain, ACL, will be greater than my open loop gain when my feedback factor K is less than 1. So essentially, what I should expect to see in a positive feedback system is a closed loop gain that's greater than my open loop gain. When we were talking about our open loop circuits, and we were talking specifically about our linear range, right? We had a really, really small linear range when we were dealing with op amps because their open loop gain was so large, right? Talking on the order of a few millivolts to even potentially just a small range of microvolts. Well, if our closed loop gain in a positive feedback system is even higher than our open loop gain, that's going to make our linear range even smaller, right? So that means that whenever we're looking at a feedback network or positive feedback system, the only possible outputs are going to be our positive supply voltage and our negative supply voltage. We are practically never going to have any linear amplification whatsoever because our linear range is so small. Okay. So one of the things that characterizes positive feedback systems is what's called their gain sensitivity. Okay. So gain sensitivity means that a small change in the open loop gain causes a large change in the closed loop gain of the system. So let's look at a quick example here. So let's say that we have a system that starts off with an open loop gain of 10, a feedback factor of 0.0999, right? So that is less than 1, which is what we want here. And let's calculate our closed loop gain based on these numbers, right? So in this case, that's just going to be 10 over 1 minus 10 times 0.0999. And we wind up getting a gain of 10 to the 4. In the second case, let's change this open loop gain by 1%. So instead of it being 10.0, let's make it 9.9. Now, do you guys think that that is a relatively small change? Because I do. 1% change isn't particularly big, okay? We're going to leave our feedback factor the same. And we're going to calculate our new closed loop gain. So that would be 9.9 divided by 1 minus 9.9 times that same 0.0999. And I wind up getting 900.819. Or to maybe to put this in a little bit better context, 9 times 10 to the 2. Okay. So what we have observed here is that changing our open loop gain by a factor of 1%, so a decrease in our open loop gain by 1% caused a decrease in our closed loop gain by 90%, right? So that is a very large amount of sensitivity that we have in a system like this, right? Our output signal is still, our closed loop gain, better way to phrase this, is still significantly larger than our open loop gain, right? 900 compared to 10, still 90 times as large, but it's not 1,000 times as large as what we saw, okay? So this is one of the principal drawbacks of a positive feedback system is this sensitivity to gain, but we can use this to our advantage, okay? So before I go on and we start looking at op-amp circuits, I want to look at one other thing just really, really quick like, okay? This is kind of an aside, but we'll use it in a moment. This quantity right here, AOL times K, is what's commonly referred to as the loop gain of the system, okay? Now, it is technically possible that we could design a feedback network such that our open loop gain times our feedback factor would be equal to 1. What would happen to that?
You get infinite hope.
So the denominator of that thing would be infinite. Or excuse me, the denominator of that would be 0, which means our output signal Y is effectively infinitely larger than our input signal X of S. Now here's where that's really interesting. If I wanted to make an oscillator circuit that didn't require it to be driven by an input, meaning that it just generated pulses, that's what I would want to do. If I want to create oscillations, meaning that I want to produce an output signal when I don't have any discernible input, I try to make my loop gain as close to 1 as possible. And we'll see that at the very end of the class when we look at what's called an astable multivibrator circuit. All right. So applications of positive feedback. The first one that we're going to talk about today is what's called a non-inverting Schmitt trigger. SCHMITT. So here's what our non-inverting Schmitt trigger circuit is going to look like. I'm going to start with my basic amplifier circuit here. So here's V plus, here's V minus, like so. And for the hell of it, I'm going to go ahead and label my supply voltages. Okay. And so since this is a positive feedback op-amp circuit, what I need is a conductive path that connects my output voltage pin to one of my input voltage pins. For positive feedback, it's always going to be connected to the non-inverting input terminal. Okay. I'm going to call this resistor right here R2, and I'm also going to place a resistor here, R1, in between my input signal, Vn, and the inverting pin. And this total network of R1 and R2 in this case is forming my feedback network overall. Okay. Now, this is comparable to the comparators that we're talking about in our last class meeting. So I'm just going to put some reference voltage here. Could be generated by an actual voltage source, could be generated by a resistor biasing network like we discussed in our last class meeting. Okay. So this is the circuit that we are going to look at. And we are going to make some assumptions here. Okay. So when we analyze this guy, here's the assumption that we're making. The input resistance of our op amp, Rn, is much larger than the values of the resistors R1 and R2 that we choose to use to bias this thing. So just like we talked about in our last class meeting, if the input resistance of our op amp is on the order of a few mega ohms, then we probably just want to put kilo ohm size resistors here. That'll be good enough to do what it is that we need it to do, okay? So just like we talked about in our last class meeting, for pretty much any reason, if we're biasing an op amp circuit, we probably want to use kilo ohm size resistors. Okay. So what we're going to do now is we're going to analyze this circuit and we're going to try to see if we can figure out what's going on. So I'm going to redraw this circuit using the practical op amp model, just like we've done in our previous classes. So I'm going to start by drawing the practical op amp model itself. So here's my input resistance. And I'm just going to leave this labeled as Rn for now. Here's V plus, here's V minus, which makes this guy right here Vd. Over here, I'm going to put the dependent source. This is going to be AVOL times Vd. Here's my output resistor, R out like so. Drop my ground down here. And now I'm going to make my external connections, right? So between my inverting input terminal and ground, I need a reference voltage. So I'm just going to throw that in as a voltage source, Vref, like so. Between my inverting input terminal, my non-inverting input terminal and ground, I need to see a resistor R1 in series with my input voltage source. So I'll have something like this. And now I need my feedback path. So I'm just going to connect my my non-inverting input node to my output node like so. And here is my resistor R2. Okay. And for what it's worth, here is the output signal of this system. Okay. So I'll let you guys catch up just a moment here. So let's talk about what our assumption does to our analysis here. We're making this assumption in order to make this system easier to understand what's going on. So if the resistance Rn is significantly times larger than the value of resistor R1 or the value of resistor R2, what does that mean about the current that's going to flow through that input resistance?
Very small.
Really, really small, right? So I'm going to say, we'll bear this out in a moment, that this current, which I'm going to label as I plus, so it's the current that's flowing into the input resistance, is going to be approximately 0 amps. So it's going to be very, very small. So if R1 and R2 are on the order of kiloohms, where we would expect to see milliamps of current, then that current I plus will probably be on the order of microamps to nanoamps, so 1,000 or more times smaller. Well, if that current is effectively 0, so very, very small, what does that mean about our differential voltage? It's approximately 0 as well. And if that differential voltage is approximately 0, then that means that our reference voltage is the thing that's being applied at our non-inverting input node, according to Kirchhoff's voltage law. Now, I know you're looking at me like he's making shit up here, but I promise we'll see what's going on in just a moment. Okay. So I'm going to now apply Kirchhoff's current law to this system. I'm going to apply KCL at the non-inverting input node, which means I'm just going to be adding this current and this current together. And we're going to see what shakes out of this thing. So if I apply KCL at the non-inverting input node, what I'll get is Vref minus Vn, bless you, over R1 plus Vref minus Vout over R2 is equal to 0. And I'm now just going to algebraically play around with this. So the first thing I might do is I might split this thing up into its constituent parts, right? So I have a Vref over R1 from the first term. I have a Vref over R2 from the second term. And now I'm going to move those negative terms over to the right-hand side. So that would be a Vn over R1 plus a Vout over R2, like so. I can pull out that common factor of Vref, leaving me with a 1 over R1 plus 1 over R2 is equal to Vn over R1 plus Vn over R2. Sorry, thank you for that, Vout. I was too busy scratching my nose because my allergies are going insane. So what I'm going to do now is I'm going to multiply both sides of this by 1 over R1 plus 1 over R2. What is 1 over R1 plus 1 over R2? R1 in parallel with R2. Absolutely right. Okay. So what this is going to do, I'll have Vref is equal to Vn. So I have R1 times R2 over R1. So that means the R1's going to go away. And I'm just going to be left with an R2 in the numerator over R1 plus R2. And over here on the Vout bit, I'll have R1 times R2 divided by R2, which means only the R1 in the numerator survives. So I'll have R1 over R1 plus R2. And this is my characteristic equation for this Schmidt trigger circuit. Okay. I'm going to put a box around this. Now, you may be saying to yourself, well, this is a weird ass equation, and you wouldn't be wrong, because when we're looking at this type of circuit, we're kind of thinking about things in a different direction as what we would normally do. What I mean by that is because we're dealing with positive feedback, our output signal is a known quantity. It's always going to be VCC plus or VCC minus. It literally can't be anything else because our linear range is so small, okay? So what we're really doing is figuring out what's the size of the input signal is that makes this thing switch from low to high. So let's go back and look at that LT spice model really quickly here. Okay. So I want us to notice something. It looks like this guy switches from low to high somewhere in the ballpark between 6 and 8 volts, right? So if we extend this 6-volt thing over, be about right here, right? So it's switching from low to high, somewhere close to 6 volts. And it's switching from high to low, maybe in the ballpark of around 1 volt. We can look at this in actually a little bit better way. If I right click on this and instead of plotting it as a function of time, I plot it as a function of the voltage at the input node. Let me just do plus n here, just so you make sure I'm not cheating on anything. We get this funny looking graph, which is called a hysteresis graph. Okay, I'm going to delete the input signal because that just has a slope of 1. And I'm going to try to explain to you guys what's going on here. So hopefully you can all see my mouse. I might want to change the color of this signal to something that we can see a little bit better on the board here. Can you guys see that pink-ish any better? Do I need a brighterish color than that? Or is that okay? Okay. So essentially what's going on in this circuit is that when my input signal is low, my output stays low until I hit what's called the upper trigger limit voltage, at which point my output voltage latches up to the positive supply voltage. And my input voltage continues to increase and my output stays the same. Well, as I back off of that output, it's going to stay high until I get below what's called the lower trigger limit voltage, which is going to pull the system down to its other stable state, where V out is equal to VCC minus, and it's going to stay low, and this cycle is going to happen over and over and over again. So I can make this hysteresis window as wide or as narrow as I want, depending on the size of resistors that I put here, okay? The only thing that I really need to be careful about is that I want to make sure that my reference voltage is somewhere in between that hysteresis window, because if I don't, it will never switch between the states, okay? So if I'm designing a circuit like this, let's say that I wanted to have it switch when my input signal was greater than 3 volts, or when it was less than 2 volts, then I should probably make sure that my reference voltage is between 2 and 3 volts. Otherwise, it will never actually switch states, okay? I'm using those numbers very specifically because on your homework, you're going to be asked to design a system that goes high when the output is higher than 3, when the input is higher than 3 and goes low when the input is less than 2. And so a really good choice for that reference voltage would be 2.5 volts, okay? All right. So what we can do with that equation that we developed is determine what our reference voltages are, okay? So in this particular case, R2 is 10 kiloohms and R1 is 3 kiloohms. So let's see how well our mathematical model that we've developed predicts the upper trigger limit voltage and the lower trigger limit voltage, which we can read off of this thing to be. So our upper trigger limit voltage looks to be about 6.8 volts, according to what's in the bottom left-hand corner. And our lower trigger limit voltage is about 0.9 volts. Okay. It's not going to be perfectly spot on because we have made assumptions, but it should be reasonably close. So, goodness gracious. So I'm just going to make a note out here to the right that we are using R1. Shit, I've already forgotten it. Was it 3 and 10? So we are going to say, let's see here, calculating VUTL. I'm just going to make a note here. The upper trigger limit voltage the value of Vn that makes Vout change to VCC plus from VCC minus, which then reminds me that I need to know what VCC plus and minus were. So let's look at there really quickly. So it looks like I have it as plus and minus 10. So I'm just going to make a note of that here really quickly as well. So VCC plus is 10 volts. VCC minus was negative 10 volts. Okay. So now I'm going to calculate this upper trigger limit voltage. So we are at a state where our output voltage is VCC minus, and we are figuring out what's going to push it up to VCC plus. So if I apply this equation, I would have, let's see, Vref is equal to VUTL times R2 over R1 plus R2 plus Vout, which in this case is VCC minus times R1 over R1 plus R2. And now I'm just going to manipulate this thing a little bit, right? So I could subtract the VCC minus term from the reference voltage, giving me VUTL times R2 over R1 plus R2 is equal to Vref minus VCC minus times R1 over R1 plus R2. And now I'll multiply things through by a factor of R1 plus R2 over R2 to give me just my upper trigger limit, right? So that'll be Vref times R1 plus R2 over R2 minus VCC minus times, in this case, the R1 plus R2s are going to cancel each other out. So this should just give me an R1 over R2 if my algebra is done correctly. And we're going to sub in our numbers here. So for a reference voltage of 3 volts, this tells us that our upper trigger limit voltage, VUTL, is going to be 3 volts. Let's see, R1 plus R2 is 13 kiloohms. R2 was just 10 kiloohms by itself. VCC minus was negative 10 volts. And then we have R1 over R2, so that's 3 kiloohms over 10 kiloohms. And when I calculate that, I got 6.9 volts. By all means, plug this into your calculator and make sure I'm not just pulling numbers out of my ass to try to trick you into thinking I know what I'm doing. Okay. So I got 6.9 volts. If we go back to that simulation and I put my mouse over this guy again, it says 6.8 volts. That's pretty damn close. Again, we did make an assumption, so we shouldn't expect exactly correct values, but we have a really good idea there. If we go back here and calculate our lower trigger limit voltage, so this will be VLTL. I'm just going to make a note here. It says the lower trigger limit voltage is the value of Vn. That makes V out change from VCC plus, excuse me, VCC minus to VCC plus. Damn it. I had it right. Sorry. Change to VCC minus from VCC plus. My apologies. Okay. Same basic equation, except now we're going to replace everywhere we saw VCC minus with VCC plus. Okay. So I'm just going to jump to the end there because it's literally the exact same relationship, right? So we could say that VLTL is going to be VREF times R1 plus R2 over R2 minus VCC plus times R1 over R2. Don't need to do that derivation again since it's literally just swapping those two things. And what we'll get is 3 volts times 13 over 10 minus positive 10 volts times 3 over 10, which comes out to be 0.9 volts, which again, if I'm remembering correctly, there's my mouse, very closely matches the results of our simulation. So now let's very briefly talk about an inverting Schmidt trigger. So how was an inverting comparator different from a non-inverting comparator? We swapped where we applied Vn and Vref. Exact same thing for an inverting Schmidt trigger. Okay. So our second application here for the inverting Schmidt trigger is going to be literally an identical circuit where we swap VN and VREF. So just drawing that relatively quickly. Feedback path up here. Still resistor R2. We've still got a resistor R1 here, but now instead of applying our input voltage on the left-hand side of this resistor, I'm going to apply my reference voltage there. And I'm going to apply my input voltage down here on the inverting input node. Now we could, if we were so inclined, redraw this using the practical op-amp model and all of that kind of stuff, but I feel that that is a complete and utter waste of our time. Because we did all of that derivation earlier to get this result. If we swap VREF and VN in this equation, that's the exact same thing as if we had just analyzed that new circuit. So I'm going to do this the lazy way and just swap those two voltages, because why the hell wouldn't I? So our characteristic equation for this guy is actually even easier to apply, because now we automatically have VN is equal to the rest of it. So we just change V out to be VCC plus or VCC minus to calculate our upper and lower trigger limit voltages respectively. So we'll have VREF times R2 over R1 plus R2. And lastly, we'll have V out times R1 over R1 plus R2. And I'm just going to draw a box around this guy. So there's our characteristic equation. Upper trigger limit is still the input voltage that causes the output to change from VCC minus to VCC plus. The lower trigger limit voltage still defined the exact same way. The voltage that causes V out to change from VCC plus to VCC minus. So the last positive feedback circuit that I want us to look at, and I'm going to do practically no derivation here, A, for time's sake, and B, because it's ridiculously annoying and it's not particularly important, is the astable multivibrator circuit. And this is explicitly going to be what's called the op-amp astable multivibrator circuit, because you can make these using transistors and stuff like that as well. So this is an interesting circuit. So I'm going to draw it really quickly, and then we're going to talk about it briefly. So I've chosen to draw the positive polarity, or the non-inverting input terminal on bottom here, just for the hell of it, okay? Let me go ahead and draw my VCC plus up here, VCC minus down here. Okay. So the first thing I'm going to do with this guy is I'm going to create my positive feedback. So I'm going to draw a wire out of here, cross like this. And this is where I'm going to put a resistor R1. And at this node right here, I'm going to put a resistor, bless you, R2. And I'm going to label that as ground. So it's kind of similar right now to one of our Schmidt trigger circuits, except that my feedback resistor is, in this case, is R1 instead of R2, and the other leg of the other resistor is grounded out instead of applying our reference voltage or our input voltage there. Okay. Now here's where things are going to get really interesting, or at least to me, it seems really interesting. I'm also going to include negative feedback. Okay. So connected between my output node and my inverting input terminal, I'm going to have a third resistor. I'm going to call this guy R. And then I've got one last component. I'm going to put a capacitor here as an energy storage element. C. Now, I'm going to label this node right here between R1 and R2 as my reference voltage. Okay. So before I run a simulation with this guy, I want to talk kind of about what's going on here. Okay. So let's assume that this circuit starts off at a state where our capacitor is fully discharged, meaning that this node right here is effectively tied to ground. So this is where we're starting from. So if our capacitor has no energy stored in it and no voltage across it, then that node is at ground because the capacitor is going to look like it isn't there. Okay. So if we assume that our output voltage is high, our reference voltage is just established by a voltage divider. So it's going to be VCC plus times R2 over R1 plus R2. Okay. So we're going to have a high voltage here and no voltage here. And so what we should see is that current is going to flow this way. And what that current is going to do is gradually cause that capacitor to charge. Well, once that capacitor charges up enough so that its voltage reaches Vref, the system is going to switch states, causing the capacitor to discharge. And it's going to gradually discharge until it hits the new value of Vref, which is just negative the voltage it had before. And it's just going to flip-flop back and forth between those two states forever. Notice there is no input signal on this circuit literally at all. Okay, so this is generating output voltages without having any input in it. What it's using is thermal energy stored in the capacitor causes it to gradually drift one way or the other until it sets up a bistable mode of operation where it switches between VCC plus and VCC minus, and it will do it at fixed time intervals, meaning that this is an op-amp version of a clock, but it's a clock that we can tune by changing the values of the components. So our frequency of oscillations is given by 1 over twice RC times the natural log of 1 plus beta over 1 minus beta, where beta is equal to the ratio R2 over R1 plus R2. So essentially, the resistor value that's labeled as R is kind of a coarse control for the frequency, and R1 and R2 provide fine control for setting the frequency. Okay. So I'll let you guys catch up, and then I'll simulate this circuit for you.
What are the assumptions made in this circuit?
None. Well, R1 and R2 need to be smaller than the input resistance, which will always be true. So let me get rid of this guy real quick and open this guy, right? So I made R1 5 kiloohms, R2 5 kiloohms, R 10 kiloohms. The capacitance 45.512 nanofarads, and I believe I set all of those numbers to give me a frequency of 1 kilohertz. So I'm just going to run this simulation, and we're going to look at a couple of the voltages, right? So let's look at V out. So it took it a little while for it to turn on. Oh, one other thing that I want to point out here. So I had to include an initial condition on the capacitor voltage here to get this circuit to simulate correctly. If I had used a not universal op amp, or if I used real components as opposed to idealized components, this wouldn't be necessary. I only put 1 millivolt of voltage across that capacitor. So it's a very, very small amount of voltage. The smaller the voltage I use there, the longer it's going to take for it to essentially turn on. Okay. Let's look at the reference voltage as well. So it's doing the exact same thing, but it's a smaller version of the output signal because it's literally just set by that voltage divider ratio. And for the hell of it, let's look at this capacitor voltage as well. So essentially, the capacitor voltage is always just chasing the reference voltage. That's what it does the entire time, okay? And because it's constantly absorbing or supplying energy to the system, it's causing the output to flip-flop back and forth at very specific intervals. If we look at the time it takes for one full cycle, so let me just click on this curve right here. So we have to just get down into the nitty-gritty. So here's the trailing edge of this guy right here, right? So it's occurring at 5.573 milliseconds. If we move to this guy over here, it's occurring at 6.573 milliseconds. So it goes through one cycle every 1 millisecond, which is indeed a 1 kilohertz clock frequency, right? So this is what like your 555 timer and stuff like that is actually based on. All right, that is enough for me for today, or out of me for today.